Hello and good day everyone. My name is John Kenneth Esteban from BS Applied Mathematics 42, and together with Ms. Jane Marie Flores, we're going to present our study entitled Graph Theoretic Optimization for the Spatial Allocation of Mitigation Interventions. So at first, we usually see problems like this as a single node. One city experiencing urban heat island, one community dealing with dengue, or one region managing epidemic cases. So when problems appears this way, the natural response is to treat them in isolation. We cool one hotspot, we control one outbreak, or we mitigate one vulnerable area. However, most real-world systems do not behave in isolation. They usually are connected in a much larger network. Now, the problem is no longer local. Cities exchange heat through atmospheric flow and urban expansion. Populations as well as vectors can move across regions, and resources, risks, and impacts can propagate through space. What we now observe here is a system characterized by connectivity, interaction, and feedback. And once connectivity exists, we also introduce the possibility of cascading effects where stress in one location can amplify risks elsewhere in the network. So at this point, a fundamental decision problem emerges. When resources are limited, how should interventions be designed? Should we optimize each location independently, or should we allocate mitigation by considering the entire system as a coupled structure? This question became the central motivation behind our study. To address this problem, we developed the Network Intervention Optimization Model, or NIOM, as a generalized optimization framework for intervention planning interconnected systems. The framework is built on the idea that mitigation strategies should not be treated as isolated local actions alone, but instead, intervention planning should account for connectivity, interaction, and system-wide influence across the network. Using a graph theoretic optimization perspective, we represented systems as weighted and directed networks where nodes correspond to spatial or functional units, while edges represent interaction pathways or influence flow between units. We have also established a formal theoretical analysis to ensure the theoretical soundness and reliability of the model. And now that we have defined the objective, we now proceed in presenting our model.
Now for our model, we developed the Network Intervention Optimization Model, or NIOM. The NIOM framework is composed of two primary optimization components. The first component minimizes residual risk or disparity after interventions are applied, while the second minimizes intervention costs under operational and feasibility constraints. One important feature incorporated into the framework is a prioritization parameter lambda that captures the systemic influence of units within the network. Because of this, the objective of the model is not simply to reduce risk locally, but to identify where interventions can generate the greatest system-wide effect across the network. As a result, intervention planning becomes structurally informed rather than purely localized. And to ensure analytical consistency, several assumptions were established in the framework. The system is modeled as a weighted and directed influence network as mentioned, while interventions are assumed to be continuous, non-negative, and uniformly applicable. Network structures and parameters are treated as static during optimization, although interdependencies still allow cascading effects across the system. And lastly, resources and efficiencies are assumed to be bounded while global scaling preserves comparability across different application domains. Beyond the optimization structure itself, we also established several theoretical properties of the framework to ensure its mathematical reliability under these conditions. For this presentation, we were only able to include the summarized results of the theoretical provings. However, if you would like to further examine, read, or see the complete mathematical derivations, formal proofs, or even the other components of the study, you may connect with us for access to the full manuscript. Now, going back, in this study, we were able to establish the convexity, uniqueness, and asymptotic stability properties of the framework under the imposed structural conditions. First, the convexity result ensures that the optimization landscape remains mathematically well-structured during optimization. Second, the uniqueness result guarantees that the framework produces a single globally optimal allocation strategy rather than multiple competing solutions. And lastly, our asymptotic analysis showed that the NIOM converges toward a stable proximal equilibrium even as system complexity and node-level metadata increase. And through these results, we were able to show that the framework remains mathematically stable, bounded, and reliable even for large-scale interconnected systems. After establishing the theoretical validity of the model, we then evaluated how the model behaves across multiple interconnected application domains.
Now for the model applications and simulations. Despite the differences in context, the NIOM framework was successfully applied across three distinct domains. The first one is for the urban heat island effect mitigation application. Second one is the COVID-19 transmission control, and the third one is the dengue fever or the vector-borne transmission application. Although each application addressed different real-world systems and intervention objectives, all simulations retain the same underlying structural and mathematical assumptions of the NIOM model. Throughout the simulations, we consistently observe highly similar optimization behavior. The NIOM repeatedly prioritized units that were structurally influential and highly connected within the network. In many cases, connectivity and systemic influence played a more significant role in allocation decisions rather than isolated local severity alone. This means that interventions concentrated in strategically influential areas were often able to generate broader system-wide improvements and indirect spillover benefits across the network. Rather than distributing interventions evenly, the framework consistently identified locations where mitigations can produce or could produce the greatest network-wide impact. We have also performed cross-domain sensitivity analysis, and the test results consistently showed that network structure and connectivity were the strongest drivers of allocation behavior across all application domains. Beyond the optimization results themselves, these findings also reveal important implications for planning and decision making.
One of the most important contributions of our framework is how it may be translated into policy-relevant and decision-oriented settings. In this study, we do not position the NIOM as a replacement for policymakers or institutional judgment. Instead, we position the framework as a decision support tool that helps planners understand how limited resources may be allocated across interconnected systems under different operational conditions. One important characteristic of the framework is that policy conditions are introduced externally through constraints rather than being embedded directly into the mathematical structure itself. For example, constraints may represent limited budgets, deployment capacities, logistical restrictions, implementation feasibility, or operational priorities. Because of this structure, the same optimization framework can remain adaptable even when planning environments change. So instead of changing the model itself, what changes are the operational conditions imposed on the model. This also allows the framework to support scenario-based policy analysis. For instance, planners may compare what happens under low budget versus high budget conditions, pace intervention strategies, expanded deployment capacities, or shifting operational priorities. Since the underlying network structure remains fixed, differences in allocation behavior can be interpreted directly as the effect of changing policy and operational conditions. And through these, we were able to translate optimization outputs into interpretable planning insights that support strategic and evidence-informed decision-making. And beyond supporting short-term planning scenarios, the framework also demonstrates reliability under increasing system complexity over time.
Another important contribution of our framework is its long-term reliability. As systems become larger and more complex, the NIOM remains stable and mathematically well-behaved even under limited resources. Its proximal inspired update behavior allows intervention to adjust gradually and predictably, avoiding abrupt or unstable allocations of resources. This becomes especially important in dynamic environments where risks, capacities, and operational conditions continuously evolve. As new risk zones emerge or intervention demands increase, the framework can adapt while still maintaining stable and consistent allocation behavior over time. And to conclude this presentation, our study have demonstrated that many large-scale real-world problems, although seemingly unrelated, share similar structural behavior when viewed through connectivity and interaction. Because of this, intervention planning should no longer be approached as isolated local mitigation alone, but a system-level optimization problem shaped by networks, constraints, and resource dynamics. Through graph-theoretic optimization, we reframed intervention planning across interconnected systems, not simply by asking where intervention is needed most locally, but where it can create the greatest system-wide impact. By integrating connectivity, optimization, operational realism, and long-term stability into a generalized mathematical framework, we were able to generate a scalable and interpretable approach for adaptive, resource-aware, and system-level decision-making in complex interconnected environments. That's all for our presentation. Thank you.